All right. What I'd like to do this lecture is go through Orthodox statistics. So I'll go through the fundamental logic of what statistics is trying to do. And I want to do that to draw out how most researchers misunderstand that logic and therefore draw wrong conclusions. And those wrong conclusions largely are about how you deal with non-significant results, how one understands the sensitivity of your experiment for picking up effects. So for the first hour, I'll present the basic logic and go into something called power, which is the most common solution to trying to understand what a non-significant result might mean. But it's, in my opinion, the least useful of the solutions on the table. And despite the fact that statisticians and statistically minded psychologists have been telling psychologists and other users of inferential statistics you should be taking into account power for decades, people haven't done so, and I think part of the reason for that is that it's not a very good solution. It's conceptually very useful to know about, and I'll illustrate that understanding what power is as a concept is extremely useful. But in practice, to analyze the sensitivity of your data, it isn't the most useful solution. But orthodoxy had another answer, and that's confidence intervals, which you've probably all heard about, but no one's ever taught how you actually use them. So again, despite decades of people, statisticians, statistically minded psychologists, and the APA, and journals saying you should be using confidence intervals, people don't. And I think the reason for that is no one's been taught how you draw conclusions that affect your theorizing using confidence intervals. So I'm going to tell you how to do that, and that is something I find useful. So that's going to be the topic of this lecture. But then I want to say next lecture that none of that is as useful as a completely way of doing things, which is Bayesian statistics. So that's what I want to introduce you to in the next lecture. Well, the basic logic of there isn't an agreed answer. There's not a consensual answer to what the basic logic of statistics should be. But the logic that became accepted in the 30s and 40s was the logic put forward by these two people, the Polish mathematician Jerzy Neyman and the English statistician Egon Pearson. You might know the name Pearson as in Pearson correlation coefficient. That was Carl Pearson, who was Egon's father. The other great statistician of the time was Ronald Fisher, and he invented most of the statistics that you use, like analysis of variance, concept of significance testing. The F test comes from Fisher, maybe picked F after himself. P less than 0.05 comes from Fisher. Concept of sampling from a population, random sampling comes from Fisher, and so on. So he invented a lot of what we now use. I mean, probably anything you use in statistics now came from Fisher, who was a genius. But when he came up with his own logic of statistics, which didn't quite work out. So he doesn't have a coherent logic of statistics, and the psychologists were influenced a bit by Fisher and a bit by Neyman Pearson. But when push comes to shove, and there's an argument about it, it's Neyman Pearson who wins because they did have a coherent logic. Now I can argue about that logic and say, from first principles, they got it wrong. They followed through from a certain set of first principles, and what we'll do next lecture is to say you need different first principles. So, as I say, this all started in the 30s. I mean, statistical procedures have been around for a while. It's just there wasn't a unifying conceptual framework to put them in. So what I want to go through now is the orthodox one, the Neyman Pearson one, that probably few psychologists have ever heard of those names, Neyman Pearson, but it's their ideas that they're using when you do statistics. And it all starts with the notion of what is a probability. Those are the first principles from which we're going to start, and we're going to go down one route this lecture and another route next lecture. So just to limber up with, use the word probable or likely in a sentence with the person next to you, and think about what the meaning of the word probable means in that sentence. Okay, so there's roughly, you can make lots of subdivisions and so on, but there's roughly two divisions of the word probable. One we call subjective, one we call objective. One is a matter of how strongly you believe something. That's a subjective definition. And the other is a matter of the proportion of times something happens in the long run. Well, that's the objective definition. So now if you're going to say the proportion of times that something happens, like I throw a dice and I say what's the proportion of times in the long run that a 6 will come up, that sounds like something objective. You could find it out, right? You could throw the dice and you could count up the times, and as long as you did it for long enough, you might be happy with the proportion that you got. You could test if a coin was fair or a dice was fair, so on, by throwing it. Something you find out about the world to some degree of approximation. Now, if you're going to do something a certain number of times, you need to define what is it you're doing and the conditions under which you're doing it. Right? That's called your reference class or your collective. It's the set of events that you're talking about. Well, proportion of what? We need to define the set of events. So probability as a relative frequency is defined only relative to a reference class. You need a set of events to get your proportion. So the events could be throwing this red dice here lots of times. Now, if you said, I think it'll probably rain tomorrow, maybe that was an example of your word probably, that's a one-off event. Tomorrow it rains or it doesn't rain. Okay. So there's no reference class. So that's a matter of subjective probability. That's a matter of the strength of your belief in something happening. There's no reference class really, it's just a single event. Right? If you said you think a theory is probably true or not, there's no reference class. That's just a matter of strength of belief. So that's subjective is strength of belief in a theory, in a one-off single event. Anytime you talk about one-off single event. So interesting, you can't say, if you say, I only want to do with objective probabilities, You can't say what is the probability that the next throw will be a 6. It's a one-off event. It doesn't have a probability. It's a matter of not an objective probability. And just to bring home the point about a reference class and that one-off things don't have probabilities, if I say, what's the probability that a person living in England has black hair? That defines a reference class, everyone living in England. Now, a given person may have black hair. If I say, what's the probability that John has black hair? That has no probability answer. That's a matter of strength of belief. You could say, well, he's English. Okay, well, that gives me one answer. As part of the reference class England, English people have this proportion of black hair. Oh, but John is Chinese in English. Oh, that gives me another answer. So John belongs to lots of different reference classes, each of which has a different probability. Right? So the probability attaches to the reference class, not to the singular events. So now subjective probabilities sound, well, subjective. And objective probabilities sound, well, objective. And if you're going to do science, which would you rather have? So Neyman Pearson said, right, we're going to use objective probabilities. So we can only talk about probabilities where we have a precisely defined reference class. So this is really said all that. So one thing we can't do is talk about the probability of a hypothesis. There is no reference class. A given hypothesis is true or false, or true to some degree, but there's no probability to attach to it. So if we're going to be in the business of statistics using only objective probabilities, we need to define some long-run relative frequencies that are of interest to us. We couldn't talk about, for example, the probability of the null hypothesis being true. Orthodox statistics cannot tell you that answer. It's not designed to. It's a meaningless question. So let's say we have some data, D, and we have a hypothesis. The hypothesis could be this drug is just a placebo cure for depression. So that's a standard sort of null hypothesis. The chemists come up with a drug. We want to test it. We set up a null hypothesis that it's just placebo. So we collect some data. We get some people, we get 50 people, and on some days they take the drug, and some days they take placebo, say, and they rate how happy they are. And then we do a t-test between the placebo days and the drug days. And we get a t-value of 2. And that's our data. We get a 2 units difference in happiness and a t-value of 2. So there's our data. Now, I've put here, we can talk about the probability of the data. This vertical line here means given. The probability of the data given the hypothesis. So given that the drug is a placebo, what's the probability that we'll get data such that t is greater than 2? What's the reference class? Well, the elements, the events in this class are the potentially billions of times we could run this experiment. So we could say, assuming the null hypothesis is true, assuming this drug is just placebo, if we ran 50 people with this design billions and billions of times, what proportion of the time would we get a t greater than 2? So that's what we're imagining. We can calculate that as a probability. We imagine millions of experiments done under the conditions of our experiment, and we ask, well, if the null hypothesis is true, how many times do we get t greater than 2? So this is a meaningful probability we can calculate. So no, we're not talking about here the probability of the hypothesis given the data. So we're not talking about the probability of my drug being a placebo, given we got certain t-values or e-values even. Hypothesis is simply true or false. So one thing a p-value doesn't tell you is the probability of a null hypothesis. And I'm not being funny. saying it really doesn't tell you that. I'm not splitting hairs over words. I'm saying those numbers do not tell you the probability of the null hypothesis in almost any way. Now, this might sound a bit confusing because you say to me, probability of H given D, probability of D given H, they sound almost the same to me. What's the difference really? So this one is called the inversion of that one, and I'll just give you an example to illustrate it can be a big difference. Let's take all the cases where a person has had a head bitten clean off by a shark. We trace them up 2 years later, and we find out the proportion that are dead. So we're looking at the proportion of dying within 2 years, or being dead 2 years later, given your head was bitten clean off by a shark. So we scale the depths of the seas, we find all the headless bodies we can, trace up newspaper reports and so on, and that proportion will be pretty much 1, right? 100%. So now let's invert it. Now we'll take as our reference class all the people who've died in the last 2 years. So we do the same thing, but we go to the morgue and open the drawers and ask the coroner causes of death and so on. And we find out the proportion of people who died in the last 2 years who'd had their head bitten clean off by a shark. So now that proportion is going to be pretty close to 0, right? Because other than the odd tourist in Australia, very few people get their head bitten clean off by a shark of all the people who died in the last 2 years. So these two probabilities are as different as probabilities come. You don't get less than 0 and you don't get more than 1. But the one is just the inversion of the other. So I hope that example makes clear that probability of A given B can have a very different value from probability of B given A. So if you ever wonder about that, just think about sharks. And next time you look at the p-value output from SPSS and you feel an instinct to assume that's telling you something about the probability of a null hypothesis, just remember that p-value is not P of H given D, it's the probability of D given H. And when you see how different these probabilities are, just think how different those probabilities could be. And the reason why I've hammered on about this, because I think, well, in fact, Oakes, as far as I know, was one of the first to propose this in a book written by about 1990, that the reason why people make such wrong conclusions based on orthodox statistics and p-values, and they don't use power and so on, is they think the p-value is telling them something that it doesn't. They think it's telling them the probability of the null hypothesis. That was Oakes' speculation. And if you thought that's what you were getting, you would make the wrong conclusion, and you wouldn't bother with power because you'd have all the information that you needed. So statistics, orthodox statistics that is, cannot tell us how much to believe a certain hypothesis. It's not its job. So from first principles, it denies that's even meaningful. All we can actually do, and this is the funny thing, is make up decision rules for certain behaviours, accept or reject. Neyman's quite clear about this. What we're going to do is we're going to accept the null or reject the null. But he said, bear in mind, this has nothing to do with your beliefs. You might have good reasons for believing things one way or the other that's different to that. What I'm telling you is that's not to do with statistics. I'm just going to give you some accept, reject behavioural rules for you to follow, even if you don't believe in the answers. And as long as you follow the procedures, we can control error rates, long-term error rates, because that's something we can give a long-term frequency to. So a decision procedure could be something like, I'm going to run 40 subjects and reject the null hypothesis if the t-value is larger than a critical value. And we can work out error rates for that. So this is the way Orthodox Statistics sees the world. divides the world typically into two states of affairs. The null is true or the null is false. And then there's two behaviours. You can accept the null, you can reject the null. Well, that means you can be right in two ways. When the null hypothesis is true and you accept it, or it's false and you reject it. But you can be wrong in two ways. And in the absence of any better names, they decided to call this one a type 1 error and that one a type 2 error. Or you could call, I mean, you get confusing remembering which is type 1 and which is type 2. You could call this one a false positive and this one a miss, if you like. But they call it type 1 and type 2. False positive, because here you're saying there is a difference when there isn't. And here you're saying there isn't a difference when there is. So you're missing out on the difference being there. Now, if there's two types of errors, we'd want to control both of them, presumably. So let's label the long-term rate at which we're making those errors. So there's the long-term rate at which you're rejecting the null when the null is true. They call that alpha. The long-term rate at which you're accepting the null when the null is false. They call that long-term rate beta. Well, that's all a bit abstract. So let's come to a concrete example. This is all the statistical tests that were done at Sussex, say, in the last year. And, of course, one never knows really when the null is true, when the null is false. But let's say godlike, we do know that. And from our godlike perspective, we know that of all the 5,000 tests that were done at Sussex in the last year, in 4,000 of them, the null hypothesis was true. In 1,000 of them, it was false. So in these 4,000 cases, there's actually no correlation, no difference between the conditions and so on. In these 1,000 cases, there actually was a difference. There was an effect. There was a correlation, and so on. Now, first of all, take alpha. I've put the little definition of alpha here. So it's the proportion of times you reject the null, given the null is true. So for these data, can you tell the person next to you what is alpha? What is the rate of a type 1 error, according to this definition here? Try and work that out from the numbers. Okay, so it's the proportion of times we rejected H0, incorrect, out of all the times that H0 was actually true. Okay. So it's 200 divided by 4,000. which would be, we could drop some zeros, that'd be 2 over 40, 1 over 20, which is 0.05, 5%. People happy with that? Yeah. So alpha here is 5%. That's no coincidence that it's 5%, because you know alpha by another name, and that's significance. Significance was Fisher's term. He hated Neyman Pearson logic viscerally, but nonetheless we use Fisher's term for the Neyman Pearson concept. They said alpha, Fisher said significance, we call it significance. And all the stats, all the stats teaching you've been taught, you say significance of 5%, and you're taught how to be strict about that, and you test all the assumptions to make sure it really is 5%. And if you did all that right, that's exactly what you'd get. You would get, if you looked at all the cases where the null was true, 5% of the time you'd make an error. Right? There would really be no difference there, and you'd say there was a difference. That's a type 1 error, a false positive. That's what significance means. It's the rate at which you are committing a type 1 error when the null is true. It's a long-run relative frequency, a long-run proportion. So this was the proportion over a year here. And hit 5% because people were testing their assumptions and doing everything right. Well, that is, significance, 5%. But I don't know if you thought about the other sort of error. Because although you've probably been taught it at some point, you don't see authors using it in papers. At least only a minority do. So now let's look at beta. That's the proportion of times you accepted null when the null was false. There's a little definition there. Just tell the person next to you what beta is in these pretend data. Okay, so here it's the proportion of times you made. We take all the times where H0 was false, so it's out of 1,000. The proportion of times you made a mistake. Okay. So there actually is a difference in these 1,000 cases. But 500 times you said there was no difference. You accepted the null. People did at Sussex last year. So that's 50% of the time. So beta here is 50%, whereas a proportion of 0.5. So one thing I hope that illustrates is even if you're doing everything right about significance, you're making 5% errors there, that doesn't control all your sorts of errors. And in fact, the other sort of error, the type 2 error, you could be making at a really high rate, like 50%. Now, I chose 50% for a reason, and that's because Cohen, a statistically minded psychologist, estimated the power a couple of decades ago in high-quality psychology journals. He estimated the beta rate and estimated it as 50%. And those 50% is typical. And there have been subsequent follow-up studies. So Cohen then went about saying, people, you've got to think about beta. You've got to think about your type 2 error rate. We can't let that be floating around 50% just because we're controlling significance at 5%. Nothing changed, and then when people have followed up, they often got 50%, often got worse than that. In a recent study, Button et al., they looked at fMRI and got an estimated beta rate of 92%. So this is why I'm talking about the way we, well, I said at the beginning what I want to talk about is how do we interpret non-significant results. The non-significant results, accepting H0, is the case, we're probably making a lot of errors. One reason we're making a lot of errors is people aren't even trying to control those errors. So that's the problem that I'm focusing on in these two lectures. The terminology people normally use, by the way, instead of saying beta, they say power. I don't know if you've heard about power. Power is 1 minus beta. It's the probability of detecting an effect, given there really is one. So it's this number, this 500 over 1,000. It's 50% here, because it's 1 minus beta. So if your beta is 50%, your power is 50%. When I said in fMRI, your beta is 92%, what they actually said was the power was 8%. Okay, the same thing. So people often use the term power. Just remember, power is just 1 minus beta. So according to Neyman Pearson, when they set up the logic in the 30s and 40s, what did they say you meant to do? Well, there's no, from the point of view of the logic of statistics, there's no answer to what alpha and beta should be. But by convention, we set alpha significance to 5%. And what should beta be? Well, I'd have thought the default could be 5% as well. Although people allow that to vary. They say, it's a type 2 error, secondary importance. Maybe 20% will be controlled well enough for that. So that's often a rate people use. So now you're meant to set those up before you run your experiment. So the question is, well, you know how you control significance. That's sort of just what you've been taught. You check your assumptions. You then, well, you look at SPSS column, and if p is less than 0.05, then you're happy, right? That's what you're doing. But how to control beta, or conversely power? Well, the only way you can assess the sensitivity of an experiment for picking up an effect is if you knew how big an effect it was that you're trying to pick up. Okay? If you had no idea how big an effect it was you're trying to pick up, you would have no idea how sensitive your experiment is. So, in order to make sure you're not making any errors, you need to know the minimal size of effect that you think is plausible and interesting given your theory is true. Once you've got that, you can, well, the old-fashioned way is power tables. Actually, you can download a free software called G-Power. Just Google G-Power. You get it, you download it. It's a little program that will then run free on your computer. Basically, your power increases with your number of subjects and with the effect size you're trying to pick up. So you type in the effect size you're trying to pick up. It will tell you how many subjects you need to run. And then that's how many subjects you need to run. So essentially, power is a way of choosing the number of subjects that you should be running an experiment, which isn't what people do. People would say, oh, in my field, we can generally do this with 30 subjects. Well, that's how we do it, and that's what people do. The problem with these rules of thumb in the field, as I say, is power has been left wildly uncontrolled. So these rules of thumb don't actually work in terms of creating sensitivity. So I said to calculate power, I must determine what minimal difference would be interesting or would confirm the theory. Now, I think that's a really difficult question to answer, and that's one of the reasons why power isn't used, just one of the reasons. But it is a key reason. What's the minimal difference that would be interesting or would confirm the theory? Well, one thing you must know is your literature. And if similar sorts of manipulations with the same paradigm or dependent variable have been done before, they produce certain sorts of effects. Well, that can give you an idea to inform you of what a minimal interesting effect size might be, a plausible minimal interesting effect size. I still think it's extremely difficult, though, to get the minimal interesting effect size, which is what you're really interested in. But that's what you're meant to be doing to calculate power. And then use the numbers of subjects that G-Power gives back as needed to have the sensitivity to pick up that effect size. That's the standard Neyman Pearson logic of what's to be done. But as I said, that isn't what most people do, and unfortunately it leads to inappropriate judgments about what results mean, particularly non-significant results. So that's what I'd like to dwell on. You read a review of studies looking at whether meditation reduces depression. So these are imaginary data. Just made this up. But I've seen lots of examples very similar to this. 100 studies have been run, and 50 are significant in the right direction, and the remainder are non-significant. So your mother is feeling a bit depressed. She says, I've heard there's something about this meditation business. You do a psychology degree. Can you tell me what? There's some meditation classes down the road. Is there any good evidence that I should try this out? So you look it up and you find this is the answer. So what do you conclude from this pattern? Just tell the person next to you what your gut reaction is. If you saw a pattern of data like these, what would you conclude about the effectiveness of meditation? Has the matter been settled yet? Can you conclude one way or the other? What's your feeling? Okay, so now a common reaction, I don't know what your reactions were, but you see in the literature and people reviewing studies, they treat it as if each significant result can be traded off against each non-significant result, as if each non-significant result throws into doubt any significant result. So a common reaction to this is say, oh, it's a bit inconclusive, really. Sorry.
No, I think they don't cancel the tag.
That's exactly right. They don't. So the common misconception, even amongst experienced researchers who've done lots of reviews, is to say, yeah, so-and-so got a significant result, these got a non-significant result. It's a bit iffy, isn't it? All right. So you're quite right. That is the most common reaction, even amongst the most experienced researchers, is completely wrong. And that is because they haven't really taken on board the logic that we've just gone through. So, if the null hypothesis were true, how many of these studies would be significant at the 5% level? So, if the just tell the person next to you, if the null hypothesis were true, how many significant results would you get? You get 5 out of 100, right? Significance is 5% significance means precisely if you had 100 studies and the null was true, you would get 5 significant. That's what 5% significance means. You would reject the null in 5% of the cases incorrectly. We didn't get 5%, we got 50%. It's the first thing I want you to think about. So now, if a null hypothesis were true, how many would be significant in the right direction? Just tell the person next to you. By the right direction, I mean meditation helps depression, doesn't make it worse. So when I said significant in the right direction up here, I mean in all those cases, meditation helped. Now, if the null hypothesis were true, it's just chance, isn't it? You get half one way, half the other way. We got 50 in the right direction. Now, if the power was 50%, which I told you was typical, utterly typical, how many significant results would you expect? 50, yes. This is just what you expect under typical conditions of psychology experiments if there really was an effect there. You expect 50 significant, because that's typical power. We don't even need an explanation of the non-significant results. We have no justification for trying to explain why some are significant and some are not. In fact, with 50 in the right direction, we are categorically licensed to conclude, according to the rules of name Pearson statistics, to reject the null hypothesis and conclude meditation is effective. But that isn't what people do, right? That's why I said understanding the concept of power is very useful. I told you very difficult to calculate what's the minimal interesting effect size and so on. But when you're looking at a body of data, just to understand power, 50% is typical, I hope that helps you evaluate bodies of evidence. And to take with a pinch of salt much of the reviews that you're going to read. Now, what would be better, and hopefully you taught this as well in other respects, is you don't count up the number of significant and non-significant results. You do something called a meta-analysis, which takes into account all the results together. Partly gets around the problem, but then what you end up with a meta-analysis is you can end up with a non-significant result. Now, what does that mean? We're still back to having to interpret non-significant results. And if people aren't doing that right, they're not going to be interpreting meta-analyses right either. The meta-analysis is only part of the solution. It's a good solution when it's used right. It's part of the solution. Okay, imagine this. I've made this up. Smith and Wang obtained a difference between conditions of 200 milliseconds on some task. There's a standard error of 100 milliseconds. They had 40 subjects, and it's just significant. Get a significant result. You say, this is really interesting. I want to replicate this. It's important work. I'll replicate it here at Sussex. So, now, they used 40 subjects. They got a significant result. Good enough for them. So I'm going to use 40 subjects. Okay. 40 subjects seems to work, right? They used it and they got a significant result. So we'll replicate 40 subjects. Now, assume, just for the sake of example, they got 200 milliseconds difference between conditions. Let's just say, by some freak of nature, that is exactly the population value. Okay. That is the effect you're trying to pick up. So let's assume, even though Wang and Smith might have been at some different university, actually, for the subjects you're selecting, there is an effect there of 200 milliseconds. There really is an effect. The null hypothesis actually is false for you to the tune of 200 milliseconds. Now they measure the standard error is a measure of variability in the data. It depends on the number of subjects and the variability. It comes to 100 milliseconds. Let's just say that they got that exactly right. The population variability you're dealing with would also be exactly the same as they got. So there is an effect there. The null hypothesis is false. What's your gut reaction about the probability you'll get a significant result? You're using the same number of subjects as they did. You're trying to pick up exactly the same size effect they did. looking through the same amount of noise that they did. Exactly the same. Just tell the person next to you, your gut reaction, what is the probability you'll get a significant result? Which is another way of saying what's the power, your gut reaction, what's the power of your experiment. Okay, so now when this sort of question is asked of experienced researchers, they'll often say something like, look, there really is an effect there. These previous guys got it. I'm using the same number of subjects. I don't know what. 95% probability I'll get an effect. I'll get a significant result. Okay? That's a typical reaction. But it's wrong. So to help you see what the right answer is, let me just remind you of something. A t-test is the mean difference that you got divided by the standard error. That's what a t-value is. The bigger the t-value, sort of the better for rejecting the null. A critical value of t is about 2. Depends on degrees of freedom, but roughly 2. So you see here they had a 200 millisecond effect, 100 millisecond standard error. That gives a t-value of 2. So I picked those numbers. So what matters to whether we get a significant effect or not is whether our t-value is greater than 2 or not. Say 2 is the critical value. Now, I said the population value is 200 milliseconds for the mean. And when you sample from a population, is your sample going to be exactly is your sample mean going to be exactly the population mean? No, it won't be. Will it? Will be a little bit less, or be a little bit more. 50-50 odds will be a little bit less, as will be a little bit more. So t is the mean difference divided by the standard error. If we had estimated the sample values absolutely, we get absolutely right. If we were bang on, we get a t-value of 2, right? That's just the cutoff for significance. But we're sampling from, so there's noise. 50-50 odds, our mean will be a little bit less than that. So will our result be significant? If our mean difference was a little bit less than the sample mean difference, will we get a significant result? No. Because significant result depends on whether mean difference divided by standard error is greater than 2. It's only if we get the mean difference bang on that we get 2. The mean difference is a bit less, our t is a bit less. We fall short of the cutoff. It's non-significant. On the other hand, if our sample mean was a bit more than the population mean, would we get a significant result? Yes. Our t-value would be more than 2. So what are the odds of it going either way? 50-50. And you can make exactly the same argument about the standard error underneath. Could go that way, could go that way. 50-50 odds. So if someone gets a significant result, just at the 5% level, and you replicate with the same number of subjects, what's your power? 50%, that's right. So let's say you see someone get a significant result. You replicate same number of subjects. You get a non-significant result. Is that surprising? No. 50-50 odds you're going to get a non-significant result even if there was an effect there. Maybe that's why psychologists typically have 50% power. They say, well, they got a significant result with 40 subjects. That's good enough for them. 40 subjects is good enough to get a result. I'm going to run 40 subjects. That gives you a 50% power. And when you have a 50% power, what does the null result mean? Yeah, not a lot, does it? I mean, what you can conclude from a null result that you basically pretty much expect 50-50, even if there was an effect there. You wouldn't really want to draw conclusions from that, would you? Jeff Cummins is an Australian psychologist who has some interesting little programs on his website. So I ran one of the programs here, captured the screen, and what this is a case where we have 50% power. There really is an effect, and the program just simulates lots of experiments. And then this side, I just want you to look at this side. These are the p-values that you get. So for the first experiment, the p-value is 0.23. Now we run the experiment again, and we get a p-value of 0.144. We run it again, 0.024. Right? Now, these successive p-values here, bear in mind, we know, because this is a computer simulation, nothing has changed from one simulation to the next, other than the vagaries of random sampling. It's not like there was a different population value, or the subjects were different, or there's no reason to explain the differences that we're getting here. This is just what happens when you have a power of 50%. So Cummins calls this the dance of the p-values, and he suggests that it explains a sort of manic depression that psychologists may be prone to when they run successive experiments. Because, I mean, look at this. 0.028, you've been trained to be deliriously happy when you get that. Right? You look at your SPSS output, you see 0.028, you're meant to wet yourself at that point. Then you run the next experiment, 0.817. Now what's going through your mind now? It's probably deepest depression. And you'll be saying, what the hell has gone wrong? And you'll be searching for explanations. And you say, it's 0.817. This p-value is so high, you probably even think that's the probability of the null hypothesis. But it's just what you expect with p-values. That's why he calls it the dance of the p-values. Look at them jump all over the place here. 0.006. The temptation is to think the null hypothesis is really, really unlikely. Maybe the probability of null hypothesis is even p equals 0.006. Okay. Next experiment, 0.476. Okay, what the hell has gone wrong? So this is the dance of the p-values. And I think it's good for your soul to look at such dances, just to bring it home to you, quite how variable p-values are, even when there really is an effect there. And one thing I want to tell you now is I want you to notice that this is not giving you the probability of the null hypothesis. That 0.8 does not mean the null hypothesis is the probability of 0.8. It really doesn't. So here's some, I'm going to finish this first hour with just some quotes, which admittedly I've cherry-picked to be dramatic, but nonetheless, these are the reactions of some statisticians. The continued very existence of significance tests is alarming. And this is the Cohen I mentioned before. After 4 decades of severe criticism, the ritual of null hypothesis significance testing Mechanical dichotomous decisions around a sacred 0.05 criterion still persist. It does not tell us what we want to know, and out of desperation, we nevertheless believe that it does. These are key inventors of meta-analysis methodology. Statistical significance testing retards the growth of scientific knowledge. It never makes a positive contribution. Meehl was a very Popperian-minded psychologist. The almost universal reliance on merely refuting the null hypothesis is a terrible mistake. It's basically unsound, poor scientific strategy, one of the worst things that ever happened in the history of psychology. So I just want to tell you that what you may have felt was a set of cookbook procedures that are set in stone are not. Okay. Underneath those stone tablets is a raging debate. And what we're going to break. Let's break for 10 minutes for a coffee. When we come back, I want to tell you what I think is the best bit of Neyman Pearson. But I need to tell you some things you weren't taught in order to use it properly. And then next lecture, we'll do something completely different. All right. Let's stop here for 10 minutes. All right, let's carry on. All right. So there's two ways of criticising orthodoxy, or the way it is in literature. One is to say that people aren't following it. So that's what I'm doing this lecture. I'm saying there is a logic there, but because people aren't following it, there's problems. Next lecture, I'll then criticise the very logic of it. Now, power, something very odd about power. You calculate power, determine sensitivity of the experiment, before you collect the data. See, that's what they said. They said you must determine alpha and beta before you collect your data. That's when you calculate power. There is something in SPSS. You might think, I know what to get my power. There's a box, an option. You say, click on power, and then it gives you this column of power numbers. That's completely meaningless. It is. It's not telling you power at all. It shouldn't be there. That's calculating power based on the data. And when you do that, you get something that is just completely determined by the significance level. It's not giving you any information other than what was in the significance level. The p-value, I mean, the p-value. It's not giving you any information other than what was in the p-value. Now that can't be power. That can't be something that's controlling type 2 errors, because you saw before in the previous example they can be wildly different. So power has this curious property that you cannot use the very data that you just collected and you got to determine the sensitivity of those data. You can't say how sensitively these data are discriminating a null hypothesis from an alternative using the data you got. So that's very odd. And I think that's a good reason to reject power as our basic method of determining sensitivity. Now, Neyman came up with something else, a confidence interval. You've probably been taught. Maybe you've calculated one. I'm going to go through how to calculate one again, just to remind you, because it is quite useful. Now, the confidence interval is better than power because you use the very data you got to determine their sensitivity. And I think you get the sensitivity in a much more intuitive way in terms of interpreting what you're meaning. So let's now go through confidence intervals. And learn to use them. What is a confidence interval? I put here a little definition. Find the set of all the values of the dependent variable non-significantly different from your sample value. Might sound slightly odd. Normally what you do when you do a t-test is you do something like, I'm going to test whether my mean is significantly different from 0. Or if the difference between these two conditions is different from 0. This is made explicit if you use SPSS for a one sample t-test. I don't know if you've ever tried a one sample t-test. There's a little box that says reference value. Type in 0. You see, you might be testing whether your data is significantly different from 50%. 50% was chance. So when you test whether your data is significantly different from something, it doesn't have to be 0. The null doesn't have to be a difference of exactly 0. Could be 50%, could be anything. So if you're, let's say you have a difference between conditions, that could be non-significantly different from 0. It will also be non-significantly different from values either side of 0. You set up your t-test to say, is my difference significantly different from 1, or 2, or 3? So let's say I measure IQ difference before and after taking a drug. The sample mean difference is 4 units. It's a drug. People seem to be 4 units higher in IQ, in the sample that is, just in the sample, after taking the drug rather than before. Now that difference that we get might be non-significantly different from 0, but it might be non-significantly different from -1 as well. It might be non-significantly different from 9. That is non-significantly different from all the values in here. All these points are non-significantly different from the sample mean. Now, when you calculate a confidence interval, you don't actually have to do this. I'm just saying this is sort of what it means. SPSS will give you confidence intervals, and you can work it out more easily. But what that means is because all of these values are non-significantly different from our sample mean, they're all possible population values. We can't reject them. These values outside the confidence interval we can reject. When we get a significant difference from something, we can reject those values. So you can reject everything 9 and above, and you can reject everything from -1 and below. But everything in here remains possible. That's what a confidence interval is. That's the way to interpret a confidence interval. Everything within the interval are possible population values, and we're allowed to reject everything outside of the interval. So now is 0 in the interval? Yes, 0 is in there. So we can't reject 0. So no difference, no population difference, that's possible. 0 is a possible population difference for these data. Now you normally say that in a different way. You normally say my data were non-significant with the factor of non-significant. What you normally mean by that is 0 is one of the possible population values. You can't rule out 0. Now, a 95% confidence interval is defined by that because if you use the procedure I'm going to tell you to use, and you use that procedure millions of times, 95% of the time it'll include the true population difference. Okay? That's what a 95% value means, confidence interval means. So I've just put in writing here, you can accept all values within the interval as possible, population values, and you reject those outside of it. So when you either get SPSS or you do it by hand, I'll show you how, it's quite simple. When it tells you the confidence interval, just remember all of those values in that interval, they are rendered still possible by your data. It's a crucial thing to remember. So if your interval is very wide, it's saying there's lots of, your data are pretty insensitive, right? Your data is consistent with a whole bunch of population values. And if your confidence interval is very narrow, it's saying you've ruled out a ton of stuff. Only these values are possible population values. You're allowed to conclude that. So you're allowed to be black and white in name and Pearson. You accept and reject. So now coming, I mentioned before, and this is the same graph we had before, his big thing is confidence intervals. So I recommend his book on the reading list, and I think I'll put up a talk by him. And it illustrates here, you get a feeling for why they tell you more than the p-value, and should help you overcome manic depression as a researcher. So what we've plotted here are the confidence intervals. There's the sample mean is the circle. The true population value is 10. You see the sample mean scatter around the true population value, just as you expect. There's 0, the null hypothesis. And these lines here are the confidence intervals. That confidence interval goes all the way from there to there. Now, I think I counted them up. There's about, well, I've got, actually, there's a bit more than 20 experiments here. And you see, this bottom one here includes the true population value. True population value is 10. This confidence interval includes it. The next one includes it. The next one includes it. Most of the time they include it, right? In fact, in the long run, 95% of the time they'll include it. And you notice here how many don't include the population value in this particular run. One, that's right. It's just this one that doesn't include it. And that is roughly 95%. So this will be typical behaviour of confidence intervals. Now, this p-value here is non-significant. What do we know about the confidence interval? Sorry. Yeah, the confidence interval, if it's a non-significant result, what is in the confidence interval? 0, that's right. 0's in it. Because 0's, we can't rule out 0. That's what non-significance tells us, is we can't rule out 0. So 0's in the confidence interval. So you just check here. 0.23, is 0 in the interval? Yes. Okay. 0.144, is 0 in the interval? Yes. Here, this is significant. 0 is not in the interval anymore. You see? Now, so you see there's a meaningful correspondence between the two sides there. But let's go back to this 0.23. If I just tell you non-significant, p equals 0.23, you might go, oh, damn it. You might say, I have less confidence in there being an effect. You might say, why didn't my experiment work? Why am I not getting an effect that Wang and Smith did? All right. Well, now let's look at the confidence interval. What are the possible values? Yes, 0 is a possible population value. But let's say we knew 10 is the population value. Let's say 10 would be an interesting value to us. Let's say we knew 10 would be, if we knew the value, if God told us the value was 10, we would say yes. Okay, that is interesting. My theory's right. If the drug improves IQ by 10 points, my God, that's interesting. Is 10 a possible value? So now when you look at this interval, what do you think? Should you reduce your confidence in your hypothesis? Should you reject your hypothesis? No. Yeah, yes, the data is consistent with 0, but yes, the data is consistent with my hypothesis. The data do not discriminate. So, here's some questions you can always ask. And this is incidentally why I'll teach you how to do it by hand. It's very easy to do a confidence interval by hand from data presented, from the summary data presented in papers. If the paper obtained a null result, does the confidence interval include interesting raw effect sizes? If it does, what does that null result mean? Not an awful lot, right? The data are consistent with the null, also consistent with the theory being true. So, if the confidence interval includes interesting effect size as well as 0, the study is insensitive and the null result is not evidence against the theory. It's one of the principles of using confidence intervals to draw conclusions. But if the interval excluded interesting effect sizes, the null result is evidence against the theory. To know if it excluded interesting effect sizes, you'd have to know the minimal interesting effect size, which is difficult. That's why confidence intervals are difficult. But we can still use them. Because even if you don't know the minimal interesting effect size, you can know that an interesting effect size is in that interval. And that's how in my published papers I've used them. I said this confidence interval is sufficiently broad, yes, it includes 0, but I know that value is interesting, it includes that as well. So here's a concrete example. Previous researchers found that asking people to think explicitly about a certain learning situation as they are learning harms performance. Okay. Reader found this genuine effect. Let's say when you don't tell people that there's something to learn there, they just sort of soak up the structure anyway. On a later test, they perform 65% correct. But when told during learning to look for the structure, they only perform 60% correct on later test. So being too explicit, conscious about learning the structure in the situation harms your learning. So let's say one of my PhD students at the time, Andy Neeler, did this. He said, okay, we'll do what Reba did, similar, but we'll ask people to consciously think about the rules after the learning, not during the learning. Reba did during the learning, but after the learning, before the test. It's a very similar manipulation. And you think probably same mechanisms at play. You get a difference between the groups, 1%. Okay, and it's non-significant. P equals 0.48. So what do you conclude about informing people about the rules and being conscious after the learning and before the test? Do you conclude anything about that? It's a non-significant result. Just tell the person next to you what you conclude about this manipulation here, if anything. Okay, so I think a common reaction is, oh, it's non-significant, it doesn't work, right? Yes, Reba gets an effect doing it his way when you tell people to search for rules during learning. Ask people to search for rules after learning, that doesn't work, non-significant. I mean, I still feel, even though I go around teaching this, giving people solutions, I still feel the instinct when I read non-significant results out, it didn't work. It's so ingrained in our thinking, in every paper we read, every talk we go to, that's what someone does. But based on what I've just told you, you know that's wrong. Nothing follows so far. Nothing at all. Now, let's say I told you this was the confidence interval on the difference. what do you think now? Just tell the person next to you, that's the confidence interval. Bear in mind, this is the original effect size Rieber got, difference of 5%. This is the confidence interval on the difference in the follow-up study. Just tell the person next to you how you interpret that. Okay, so the confidence interval includes 0. That's what it means to say it was non-significant. But it also includes 5%. And we just concluded 5% was interesting, because that's what Rieber got. So nothing follows from the experiment. We just don't have sensitive enough data yet. As you run more subjects, your confidence interval will shrink. So you need to run more subjects until it shrunk to a point that it was discriminating. Incidentally, I describe this in my book. Instead of doing power to do sensitivity, you could decide in advance, I'm going to run until my confidence interval is a certain width. So you know it's going to discriminate. Okay. As you run subjects, you'll bounce around a bit, but basically you'll shrink, you'll shrink, you'll shrink, you'll shrink. Then you can stop when you know it's discriminating enough. Okay. So how do we calculate the confidence interval? You need to know the mean difference between conditions, and you need to know the standard error. Right, so how do you do that? Remember, and this is something worth remembering, just sort of committing to memory, a t-value is a mean difference divided by the standard error of that difference. T-value is a mean difference divided by standard error. Means we can rearrange that. To get a standard error, you just take the mean difference, which any paper should give you. Just occasionally you see a paper that just reports p-values or something, doesn't tell you the means. That is really bad practice. I mean, the policy of all journals is you always report descriptive statistics. So that should be there. So you should be able to see what the mean difference is. It was 50 milliseconds, it was 2 units on the Likert scale, or whatever it was. And they should tell you, we're talking about confidence interval is broader than t-values, but I want to stick to t-tests just because they're very common, very useful, and teach the concepts with that. So if it's a t-test situation, they should give you a t-value, right? So the paper gives you the t-value, or if it's your own data, you can get the t-value with SPSS. The standard error that you need is the mean difference divided by t. Bear in mind there's lots of different standard errors. There's the standard error of the mean, there's the standard error of the difference. The right standard error that we want for this situation is the mean difference divided by t. So generally when you're looking at a paper, you'll be able to get that. You'll be able to get the standard error. I often do this, by the way. I often go through papers and get things out of them just like this to calculate confidence intervals or Bayesian analyses. And you don't really need more maths than this. Now the other thing you need to know is the critical value of t. So I've given you a link to a website here. Where is it? And I've called it up. To use the website, the crucial thing is the degrees of freedom. So the paper should tell you the degrees of freedom relevant for that t. Or if you do SPSS on your data, it will tell you degrees of freedom. So let's just say it was 39. And you click find. and then it gives you the critical values. Now, what you're looking for, I mean, generally we're going to work at 5% levels. You use the 5% significance for a 95% confidence interval. Right? You'd use a 1% significance for a 99% confidence interval. That's the way it works. Let's stick with 95%. And for the assignment, we're talking about 95% confidence intervals. So you're looking at 5% significance, and you always look at the two-tailed case to do a confidence interval. It doesn't matter if you think this was a directional hypothesis, should have been a one-tailed test, or even if they used a one-tailed test. For the sake of getting your confidence interval out, use the two-tailed test. Okay? So it's just this first box here. You'll always go to that first box there. Tells you the critical value. It's about 2.02. So hopefully that's straightforward. There's a link there. So I put here, always look at the 0.05 two-tailed box to get a 95% confidence interval. Then the rest is easy. The confidence interval goes from here to here, so you have a lower limit and an upper limit. The lower limit is, take the critical value of t you just got from that program, is about 2. Let's multiply by the standard error. So it's roughly twice the standard error. Mean difference minus twice the standard error, that's the lower limit. Mean difference plus twice the standard error, that's the upper limit. When I say twice, I mean the critical value of t. It will be about 2. Does that make sense? So it's quite easy to do. And if you're in any doubt about the critical value, just use 2. Often you can do that in your head just as a quick check. It'll be close enough to 2. That's how you calculate a confidence interval. So it's quite straightforward. I mean, if you have your own data, you just ask SPSS to do a t-test. It automatically gives you the confidence interval. But if you're looking at a paper, you just follow this little procedure. Hands up if you think you can follow that procedure. Does that seem straightforward? Okay. So we'll just go through a concrete example. Let's say a paper gives you, and this is all you need to know, a difference between conditions, say it's 210 milliseconds, and a t-value. So it might say t19 equals 1.68, and it says it's non-significant. So there's a non-significant difference. So that's typically what you can get from the paper. That's all we need. That'll be all we need for the Bayesian analyses next lecture. It's all we need for the confidence interval we're dealing now. So the t is the mean difference divided by the standard error. Thus, standard error is the mean difference divided by t. So the mean difference here, they've told you, is 210 milliseconds. Divide by the t. 125 is the standard error. Now we've got our standard error. If we went to this site and said it was 19 degrees of freedom, you see the 19 was here in the brackets. That's the degrees of freedom. It says the critical t is 2.09. So you can check this later yourself, make sure you've got it. So we can work out the lower limit, minus 51 milliseconds, and the upper limit, plus 471 milliseconds. That's the confidence interval. So what these data are telling us, according to logic of confidence intervals, any population difference between those limits is possible. We can't rule it out. But we can rule out values beyond those limits. We say, no, it can't be that extreme. It couldn't be 500 milliseconds. We'll rule out minus 100 milliseconds. But within those limits, we say, it's possible. So remember, it goes from minus 51 to 471. That's the interval that we've got. Here's some questions. If the t-test is non-significant, as it was in that case, what do you know about the confidence interval? Tell the person next to you. Okay, 1. If the t-test is non-significant, here's something we know about the confidence interval, includes 0. Right? Now, we had an interval that went from minus 51 to plus 471. It goes all the way up to 471. Includes 0. Well, we knew that because it was non-significant here, right? See, minus 50 to plus 471 includes 0. Now, just bear in mind it goes up to 471 for the second question. Now, let's say we're predicting a difference, and previous studies we think are relevantly similar, and they had found a 400 millisecond effect. Does this non-significant result count against that theory that we have? Just tell the person next to you. Okay, so here the interval includes 400, right? So the data are consistent with the theory. They're consistent with the null hypothesis, but they're also consistent with our theory. They don't count against the theory. They don't count against the null hypothesis, but they don't count against our theory. How often will a confidence interval include the true population mean? Test of your memory. Tell the person next to you. Okay, so a 95% confidence interval, which is what we're dealing with here, we include the population mean, the true population mean 95% of the time. That's what it means to say 95% confidence interval. Included 95% of the time. Now, I've changed the word here, population, to sample. How often will a confidence interval include the sample mean? Tell the person next to you. How often will the confidence interval include it? People often get this wrong, by the way. Just think about it a bit. There is an obvious answer, but just think. All right, so the procedure for calculating a confidence interval is you take your sample mean, we take off twice the standard error, that's one end. We add twice the standard error, that's the other end. What's always between? Sample mean, yeah. So, how often will the confidence interval include the sample mean? 100% of the time is absolutely guaranteed. It means absolutely nothing. Now, the reason why I say this is sometime in the assignment people will say, confidence interval included the sample mean, therefore the theory is right, or something like that. Bear in mind, the sample mean being in the confidence interval means nothing at all because it's guaranteed. Sample mean is always going to be a possible population value, isn't it? It's your best estimate of the population value, so it's always in the confidence interval. What's important is not whether the sample mean is in there, it's whether the interesting values are in there. 0, 400 milliseconds, whatever. The theoretically determined values, that's what you're asking, are they in that confidence interval? So, you've probably been taught how to do confidence intervals. Yeah? You've probably been told the great stuff. You've been told the great stuff before? I just did, I know, but beforehand, in your stats classes before you met me, did they say confidence intervals are great stuff? No, looking a bit doubtful. Maybe they did. Well, psychologists have been told for a long time the great stuff. The American Psychology Association has had various statistical task forces that give recommendations. those task forces have said, use confidence intervals whenever you can. There was a, blanking his name at the moment, there was an editor of a psychology journal who said for his tenure of chief editor, you must report confidence intervals when you submit to this journal. People dutifully did. As soon as he ceased to become editor, they stopped. And despite the fact that the APA says report confidence intervals whenever you can, nobody really does. And despite people who told us great stuff, nobody really reports them. And I think the reason is if a confidence interval was just something else you reported in the results section that didn't change how the discussion went, then what's the point? It's just extra verbiage in the paper. So what we need to know are what are the principles of drawing theoretical inferences by reference to intervals. And that's what's been missing, I think. So here are 4 principles of inference by intervals. What we need to do is to use confidence intervals. We can't have a point null hypothesis if we want to be in a position to accept null hypotheses. Let's take any interval at all that includes 0. That's non-significant. What else does it include? Positive differences and negative differences. A confidence interval, if it includes 0, will always include as well differences. You're always going to get an interval. You have to have an infinite number of subjects to get a point. You've always got an interval. If 0 is somewhere in the middle there, you've got positive differences, you've got negative differences. That means differences are always consistent with your data. So how can we ever assert a null hypothesis? Well, what you can do is, and in a way, you're meant to do this anyway in terms of power, is decide what's a minimal interesting value. Are there some values so small you would say, yeah, I mean, if meditation reduced depression by that amount, forget it, it's not worth it. And often in a clinical setting, in applied settings, not often, but sometimes, people have come up with minimal interesting values. So I think for depression, they say the difference has to be more than 3 units on the Hamilton depression scale. Something like that. It's less than 3, it's not interesting. It's not clinically interesting. So now, what you end up then with is the null region hypothesis. So this is a slightly different way of thinking. If your confidence interval fell squarely in the null region hypothesis, well, you can reject any interesting differences. So here you would say, if this was a treatment for depression, you can say, you can assert the null region hypothesis. You can say the treatment is not effective, at least not to a clinically important degree, because the interval is completely within that region. If the interval is completely without that region, you can reject the null region hypothesis. So it only includes interesting values, damn fine treatment. But if it included uninteresting values and interesting values, the data insensitive, suspend judgment. So I think this is extremely useful for all research. Sometimes I've had people on the clinical masters say, why are you teaching me all this statistics, Zoltan? Just to give you an example, I read a book about alternative therapy, chiropractic, acupuncture, so on. All that book told me was it was a non-significant treatment for this and a non-significant treatment for that. At the end of the book, I knew nothing. Just being told it was non-significant tells you nothing. I had no idea whether I should go to a chiropractor to fix my back or not. Because being told something's non-significant is to tell you nothing at all. And yet people draw conclusions on that about the effectiveness of therapy. All right, now we can relate something, we can relate this we've been talking about to the Popper section about falsifiability. what pattern of results could falsify the following theories? So one. So let's say the theory is group A will score higher than group B. Just tell the person next to you what would falsify that theory. Okay, so the theory is group A will score higher than group B. If group A scored significantly lower than group B, would that falsify the theory? Yes. Yes. You look very doubtful now. I'm going to tell you whatever you say is wrong. So, but remember, when A is significantly less than B, you are licensed by orthodoxy to say that's how it is. A performs less than B in the population. So that falsifies the theory. What about a non-significant difference between A and B? Would that falsify the theory? No, that's right, exactly. Yeah. A non-significant result would not falsify the theory. Because your confidence interval, if 0 is in it, will include positive and negative differences. So if all the theory is A is higher than B, it won't be falsified by a non-significant result. All right. Group A will score differently from Group B. What, if anything, falsifies that? Tell the person next to you. Okay, Group A will score differently from Group B. Let's look at these possible patterns of confidence intervals. Do they all include differences? They all include differences. Even the cases where there's non-significance, confidence intervals include differences. Differences will always be consistent with your data and analysed in an orthodox way. Nothing falsifies too. It's an unfalsifiable theory by Orthodox Statistics. A non-significant result does not falsify too. Nothing does, if you use Orthodox Statistics. With Bayes we can, by the way. Bayes we can do better. But any papers you're looking at, we're probably not using Bayes, using Orthodoxy. Okay, 3. Group A will score the same as Group B. Tell the person next to you what pattern of results would falsify that. Yeah.
Why doesn't the second one, if they score the same, why doesn't that falsify it?
All right. So here's a confidence interval where they scored the same on the sample. Remember, we're interested in the population. These are the set of population values. Are there differences as possible population values?
Yeah.
Yes. Yeah. So, since an interval is always an interval, it always has length, it will always include differences. Your data are always consistent with there being population differences.
If they repeatedly falsify
well, then your interval shrinks, but it never goes to 0. Your interval will always include population differences, even if the sample mean is 0. Group A will score the same as Group B. That's falsified by a significant difference, either way. So 3 is falsifiable. Bear that in mind when you do the Popper section, these points I've made. All right. So this is the assignment for the orthodoxy. Have the authors determined what minimal difference could be expected if the theory were true? Because remember, you need to do that to do power or confidence intervals. And the answer probably is no, they didn't. Okay? Because who does? Or maybe if you pick some paper under pressure or something, they might have done. Some papers might. But probably they didn't. Then I ask you to estimate an effect size you would expect in this situation. So I've chosen papers to do this where that you don't have to go hunting for lots of things. It'll be in the paper. I've told you a paper you can use to get an expected difference. Okay. You use a previous study that did something very similar and you say, okay, that's an expected. I roughly expect to get the same again. But now, the more difficult question is, what's a minimal interesting difference? See, there's the difference you roughly expect, but then there's the minimal interesting difference. Now, really, there isn't an objective way of getting that. You have to reach deep into your soul and say what you feel like. Okay? Maybe you can do that. Yes, meditation, that'll help. Now, have the authors established their sensitivity to pick up such a difference through power confidence intervals? Probably not, but they might have done. Some papers do. So then I ask you to use to calculate a confidence interval and to argue whether or not the data sensibly distinguish the alternative from the null, using those rules I've just gone through. All right, there's someone banging on the door here. So I'll see you all next week.